to Super Prof. This is the fourth video lecture on the diode circuits. Okay, today we'll see some more problems on diode applications, diode circuit basically. I hope you are getting the concepts. In the last class we have done the problems on clippers. We have seen the clampers. The clipper is used to cut the waveform and clamper is used to shift the waveform. In the clamper we'll add the DC part to the waveform. In the clippers we'll cut the waveforms. Okay. So clampers also we call it the DC restorer and the clipper is the cutter, right? So today also I'll start my session with problems only. One very interesting problem is given. This is the GATE 2016 1 mark problem. Let me start the session. So the problem is given 1K resistor connected with 3 volt of battery and in series connected diode D1. Let's take it D1. Here I have 5K resistor like this. The circuit is like this. Across the 5K resistor I have 1 milliampere current. Okay, this is your question given. 2 points they have mentioned, A and B. And their question is, the diode D used in the circuit below is ideal. The diode D1, the condition given is ideal. It's ideal diode, okay? The voltage drop VAB across the 1K resistor in volts is, your question is, you have to find VAB in volts. So this is decimal something types of question. You have to fill your answer over here, right? So friends, this question I can do in 3 ways. I can do in 3 ways. I'll tell you all 3 ways so your concept will be crystal clear how to solve the circuit. Let me start with my first way, right? The first way to start is in the electrical circuit. You all know we studied the source transformation. In the source transformation, what we have seen, we can convert the voltage equivalent circuit into current equivalent circuit and vice versa. I can change the I into V also. If you want to convert the voltage circuit into the equivalent current circuit, what you need to have is, you should be having one voltage source in series with resistor R. Is it okay? This one only you can transform into the equivalent current. The equivalent circuit of this voltage source will be given by one current source in parallel with resistor R across the same point, whatever point is given over here. Across the same point, the equivalent circuit of the voltage circuit is given as in the form of current. What will be the value of this current? V equal to Ri by Ohm's law, I can give it, and V equal to Ri. So I equal to this current will be V by R. Here V is this, R is this, and this R is same as this one. Okay, so this is the equivalent circuit. So I can apply the source transformation technique over here also. Let me erase it and let's come to the question part. Okay, see in this question, if you will see carefully, the 5K resistor is connected in parallel with current source. So can I convert it in the form of voltage source? Yes, easily I can convert it. If I'll convert this part into equivalent voltage source, so it will be, this 5K will come into the series, this is 5K, and in series with voltage. Is it okay? And voltage is given by V equal to Ri. You need voltage, so you have to multiply these 2 terms. So this will be 5 volt. So this entire thing you can replace by this voltage equivalent circuit. So can I remove this from the circuit? Yes, I can easily remove this and will replace by this circuit. Whatever you have found, you can replace it, right? So this is all about the source transformation, if you know about that. Okay, so this is your new circuit. Now it's with very simple questions. Why this is simple question? So at this terminal 3 volt is given. At this terminal 5 volt is given. If you find out the current in the circuit, so obviously the current will move in the circuit from higher to lower potential. So direction of the current will be like this or not? Tell me. Here I am not interested to find the current value. If I know the D1 is off, see, In which condition D1 will be biased? It will be in reverse bias. In the reverse bias, the current direction is negative to N type to P type. Is it okay? In the forward condition, the current will flow from P to N. This is the forward condition. But I encountered with reverse bias condition in this question. It means D1 is off. Are you getting me? If D1 is off, friends, so your circuit is like, let me erase some part and make it simple and clear for you. If you identified that your diode D1 is in off state, you can remove this from the circuit. Your circuit is open. If your circuit is open now, tell me, is there any current in the circuit? Is there any current in the circuit? If you want to flow the current in the circuit, you need to be close it. The circuit should be closed, then only the current can pass into the circuit. Here, I don't have any circuit, so I equal to 0. If I equal to 0, will there any voltage drop over here? Let's take voltage drop VAB. So VAB you will give by R into I. Your R is 1K. Tell me the current. Current is 0. So it's 0 volt, friends. So VAB is 0. You have to write over here 0 volt and you will get your marks. This is the GATE 2016 problem. Okay. GATE 2016. Now I told you earlier the same question I can do by 3 methods. So the first one is over. Let's come to the second one. Okay. And the second one is, let me clear some part. Okay. Again, I will throw it. So the question given is 1K. Okay, 1K connected with a diode D1. Here the battery is 3 volt and here it's connected with 5K and 5K itself is connected with the parallel current and that is 1 milliampere like this. Is it okay? Like this. So this is your circuit given and the question is same. You have to find out the voltage drop across A and B. This is the point A and this is the point B. They're asking VAB in volts. Okay. So what is the second method? This is the second method. Okay. In the second method, earlier I told you that how to solve the diode circuit. If any diode is given in the circuit, let's assume it short circuited. Okay. I told you. This was the method I mentioned in the last question, that how to solve if you are getting diode in the circuit. Okay, let me erase some part. So our assumption is we have to assume diode is short circuited. Diode is short circuited. This is your assumption, right? This is your assumption. If your assumption will be wrong, it will be, you can find out it in the equation. How? I have taken here, see, the diode is short circuited. Now let's take some current in it or assume some voltage over here. Let's take it V. Is it okay? So now I can apply the nodal analysis over here. If you'll apply nodal analysis, it will be V minus 3 divided by 1K. Am I right? Yes, this part is over. Now what about this next? This is V divided by 5K. What about this? 1 milliampere is incoming current. This is 1 milliampere equal to 0. If you'll solve this, V minus 3 divided by 1K plus V by 5K equal to 1 milli. Can I write it? Let's take LCM over here. It will be 5K. So it will be 5V minus 3. Is this 1K? Yes, 1K and this 5K. 5K is the LCM. Here 5 will be there. V minus 3. It's correct. Plus V equal to 1 milli. So you will multiply this 5K with this. So you will be remain with V minus 3 plus V equal to 5. So this will be 5V minus 15 plus V equal to 5. So overall 6V equal to 15 plus 5, it's 20. So V equal to 3.33 volt. Now this is the condition. Whatever you assumed in the circuit, by that assumption you are getting the voltage at this node is 3.33. 3.33 you find out. Now if this is 3.33 and this is the 3 where the current will flow in the circuit, and why I am calculating the current in this, because I need to know the situation of diode, and diode is given in this branch only. So initially the diode was given in this direction. In the diode the current is reverse bias, so definitely this diode is reverse bias. What it indicates? It indicates that whatever I assumed for this circuit is completely wrong. My assumption is wrong. I had to reverse myself now. I assume the diode is forward bias. Now I'll correct myself and I will open the diode circuit, or I'll assume that diode is reverse bias. I hope it's pretty clear to you. Okay, so let me erase some part. Let me make it very clear. So according to your equation, whatever you solved, you get that diode should be in reverse bias. Okay, fine. Let's keep it open. This is open circuited, or you can say in other words, the reverse bias current. In the reverse bias current, will there be any current in the circuit? No, current will be zero because circuit is the open. If circuit is open, will there any drop? Let's take it. VAB is nothing but 1K into current in it. So 1K into 0 is equal to 0 volt. Again, the answer is 0 volt. Your 1 marks. This is 1 mark question in 2016. So you are getting your 1 mark if you are getting 0 output. This is the second. And come to the third one. Why I'm telling you all these three? Because it will be very important to know about all these three. And this third one is very, very, very important because in the next step, we are going to use it. Okay. Again, I'll draw in 30 seconds. 1K. This is 3 volt. This is your diode. Okay, fine. This is 5K. And in 5K parallel with 1 milliampere, the question is find out the VAB. Where is the AB? Across this. You need to calculate VAB, where A is the point over here. The question part is over. They're asking VAB in volts. Okay. So in my first, I did the same thing by source transformation technique. In the second, assumption is diode. I assume forward bias. In the third case, in third assumption D1, I'll assume it's open. Open means not present in the circuit. Not present in the circuit. This is my assumption. This is very important. When we'll solve the general diode questions, this concept will be very useful. So please remember it and please focus whatever I'm telling you over here. In the last techniques, in the second method, what we assumed is the diode was short circuited. Here assume that diode is not given in the circuit. And the rest of the things are pretty as it is, right? 1K is given over here. The diode is not over here. Just assume this. These 2 points are given and we don't have any diode circuit over here. So what we have to do in the open circuit, please take the voltage over here. Please find out the voltage at this point. At this point, if this is open, this 3 volt is coming over here. Is it okay? See, if the circuit is open, no current is flow. So entire 3 volt be there at B terminal. This is B. 3 volt is given over here. If you will find out the voltage over here at the point A, it will be very easy to find out that if you will apply the voltage, if you will come with the diode over here between A and B, will it be in reverse bias or the forward bias? So friend, this is all about the open circuit. This entire current 1 ampere is coming to this. 1 ampere into 5K, this will be 5 volt. Now see the situation. The point B is given as 3 volt. Point A is 5 volt. Now your task is to apply your voltage over here. You have to apply your diode over here. Your diode is coming in this way. Now tell me friends, what will be the condition of this diode? Definitely it will be reverse bias because at the negative terminal of the diode you are having 5 volt. At the positive terminal of the diode you are having 3 volt. Definitely the diode will not work. Now you have to go through with it. This condition, whatever you have found over here, that your diode is in the reverse bias. In the reverse bias your diode is, there is no current in the circuit. Finally at the output, whatever he is asking, VAB is nothing but the voltage drop in 1K. 1K multiply with 0 volt. You have to simply write over there 0 volt. This is all about the questions. It's very easy. Now I'll take another problem and it will be also very easy for you. Okay. This is GATE question again. GATE 2012. Okay. And the question is the question given the circuit 1K connected with 10 volt and given over here diode, let's take it D1. The voltage drop in the diode is mentioned over there in the question V, and the current in the diode is also given I. Is it okay? This is your question. And what the question is the IV characteristics of the diode in the circuit given below are, IV characteristics is given like I equal to this I. This is the I. This I is given V minus 0.7 divided by 500 ampere, and the condition is if V greater than 0.7 volt. If this V is greater than 0.7 volt, the current flow in the circuit will be this. Else it will be 0 ampere, and the condition is V less than 0.7. Definitely the diode will be in cutoff region, and in the cutoff region there will be 0 current in the diode. Okay. So the condition is given, the IV characteristics of the diode circuit is given. This is the particular diode. They are saying I will be V minus 0.7 divided by 500 ampere when V is greater than 0.7 volt. Okay, fine. Now what they are asking, the current is. The question is, the current I is. The question current I is. The question is like this. Okay, and the options are given. The A is 10 milliampere. Option B is 9.3 milliampere. Option C is 6.6 milliampere, and the last one is 6.2 milliampere. So friends, how you will proceed in this question? This is the simple, very simple. See friends, so if you see this circuit or this question, it will be looking like tedious, but it's very easy. See, what is the current over here? Directly given, the current is 10 minus V, 10 minus V divided by 1K. The current is given or not? Simply 1. What is the I? Potential difference divided by resistance. This is your equation 1. This is your equation 2 given over here. I equal to V minus 0.7 divided by 500. This is equation 2. You are having two equations and two unknowns, and they are asking for the I. This is a very simple circuit now. So let me replace V value because I need to calculate I value, right? So the V value by equation 1 is 1Ki, fine, equal to 10 minus V. So V is 10 minus 1Ki, simple. Okay, just replace this V over here. So let me take over here, I is nothing but V, tell me 10 minus 1Ki. 10 minus 1Ki minus 0.7 divided by 500. Divided by 500. This 500 will go this side, so this will be 500 I equal to 9.3. This is 9.3 minus 1Ki. This is 1Ki. 1K will go that side, so it will be 1.5K I of 9.3. So by this equation, your I is 9.3 divided by 1.5 milli. So it will be like this. So it will be 93 divided by 15 milli. So 15, 6, 19, 6 will be remain with 3. So it will be 2 milliampere. What is your answer? This is the answer. So this is the problem looking like very tedious but very easy. You can see over here. The equation 1 is given already. You are making another equation by looking this circuit and you are getting your answer. Okay. So this is all about this part. Now let me take another problem. So this is the gate problem of 2013. Gate problem 2013. Okay. And the problem reads as, you have circuit, very tedious circuit looking like, but it is not in actual. Okay. They are connected. 4 diodes are connected in this way. Over here, 1K plus minus some drop is given over here, and this is looking like this. Here you have 1K connected with Y, and here you are connected with the Z. This is your W, and this is your X. The diodes, 4 diodes are connected in this way. It's looking like they are making bridge circuits, but the terminals are open, W, X, Y and Z. Y is connected with 1K. Here is the 1K is given. Now the question is, a voltage 1000 sin omega t is applied across YZ, across Y and Z, across YZ. Okay, 1000 sin omega t voltage is applied to YZ. Fine. Assuming ideal diodes, the diodes are ideal. The diodes are ideal, right? Now the diodes are ideal. The voltage measured across W and X is, they're asking find out WX and WX, they're asking find out VWX. Okay, so how to proceed it? Okay, let's start it. So let me change the pen. Okay, fine. Here this is the YZ. Okay, I'll make it clear. Okay, so here we are applying the input part, right? Input part. Now it is the sine waveform having magnitude 1000. You are having sine waveform like this, max value 1000. This is V, this terminal was YZ, VYZ, right? So it has two halves, positive halves and negative halves in entire one cycle. Now the question is, what is the VWX? See friends, if I'll apply this to Y and Z in the positive half cycle, what will be the situation? Tell me. This terminal at positive potential and this is at negative terminal. What will be the state of this D1 and D2? If this is D1, this is D2, let's take it D3 and this is D4. The positive terminal is connected to the N part of the diode, so they will be in reverse bias. This will be in reverse bias. Okay, what about this two? The negative terminal of the battery is connected over here, so let's assume, or they will be definitely in reverse bias. So all diodes are in reverse bias in the positive half cycle of the input 1000 sin omega t. Is it okay? If all are open circuit, so VW and VX will be same or not? Tell me. All are open circuited, no voltage is there. Whatever voltage is there, it's same, 0 volt. So they're asking VW minus Vx, and that is 0 by this equation. So in this case, the case when positive half cycle chosen, when you choose the positive half cycle, your answer is 0. Let's come to the negative half cycle now. Let me erase some part over here. Now in this case, what we are going to do is, we'll see the negative half of the cycle and we'll see what is the changes are coming over here. Okay, let me take it. So now we are applying this terminal as negative and this is positive. When you are applying this negative and this positive, this both diode will be in forward bias. It's like this. This will be in forward bias. The two are also in the forward bias. Your circuit is become short circuit. Is it okay? This is simple short circuited circuit. If this is the short circuited, the voltage is W and the voltage at X will be same or not? VW equal to Vx. Will it be or not? Tell me. If they are short circuited, whatever voltage will be here, the same voltage will be here because they are short circuited. Okay. So in this case also, VW minus Vx will be 0. So Wx is 0. So your final answer is 0. And you have given with the 4 option. A is sin omega t. And 2 more options are given. And at the D stage they are giving 0 for all t. So you have to do this. That you are getting 0 for all t's. Is it okay? So I hope the questions are pretty clear and concepts are pretty clear to you. Now let's take the next topic, and that is the voltage doubler, right? Wait a minute. This is the voltage doubler. Friends, as the name given over here, this is the voltage doubler. Means this is the device or something which will double the voltage. Whatever you are going to apply, it will double it. Okay? Yes, friends, this will double the voltage, the input voltage. How it will double the voltage? See, this is the circuit given over here. I'll use the capacitor circuit. Whenever you want to double or shift the input, you have to add some capacitor in the circuit, because capacitor is the element who store the energy. So in the later stage, we can use that stored energy by shifting the waveform or by doubling the voltage, doubling, tripling or whatever. Okay. Sorry. So friends, how this circuit will work? Let's see the circuit first. 10 volt input. This is the sine waveform or AC waveform I can say is applied to this circuit, connected with C1, and this is connected to D1. Again the circuit is D2 connected with the C2, and output you are taking at this stage. Friends, if this will be 10 volt, at the output you will get 20 volt. This is the magic, right? We are applying the 10 volt and getting 20 volt. How? Who is the magician? These two, C1 and C2, they are the magician. They will store something and they will apply at the output 20 volt. Okay. So this is the trick over here. So let's see the trick. A voltage doubler circuit is shown in the figure. The circuit produces a DC voltage which is double the peak input of the voltage. See, it will introduce only DC voltage. At the input stage you are having which voltage? AC voltage, right? But at the output stage you will get the definitely DC voltage only. Right. See, in the AC circuit, if your input is like this, this is your input, okay? Let's take it VINT. VINT is given. So this is the max value. If the max value is VM, at the output you will get 2 VM. This will be your output according to this circuit voltage doubler. So the circuit produces a DC voltage which is double the peak input voltage. Peak input voltage. This is the peak voltage, okay? At the peak of the negative half cycle, D1 is forward bias. This is the working, okay? So let me clear some parts, then we'll discuss about it. So friends, so at the input stage, I'm taking one waveform. Let's take it like this, okay? This is given 10, this is the max value, and actually it's given 10 sine omega t volt. Okay, this is voltage waveform given over here. See, this is the positive half of the cycle, this is the negative half of the cycle. Now, what is the working over here? See friends, at the positive half cycle, if here your input is positive, a positive half cycle, this will be in reverse bias, okay? This circuit will basically start with the negative half cycle. See, at the negative half cycle, the peak of the negative minus 10, who will be in forward bias? Definitely the D1 will be in forward bias, okay? I'm talking about negative half cycle. Let's take first the negative half cycle over here. In the negative half cycle of the input, the diode D1 will be in forward bias. Is it okay? Forward bias. At that time, the D2 will be in reverse bias. If this will be reverse bias, so this circuit will be in cutoff in the negative half cycle. So what will happen? This capacitor will going to start the charge itself, right? Up to minus 10 it will charge itself in this way, because this side you are applying the or you are talking about the negative half cycle over here. So up to the peak value it will charge itself. Now what will happen when the input change its cycle or its a half? Okay, the first part is clear. The capacitor is charged now. Okay, and now we cleared all this negative portion and we entered to the positive terminal or positive half of the cycle. When the positive half cycle positive of the cycle will start, what will happen, you know, in the reverse bias the capacitor is charged up to 10. At the time the D1 was forward bias, but when it will be positive half cycle, when it will be entered in the positive half cycle, suddenly this thing will be off. Is it okay? The D1 will be off because D1 will come in the reverse bias now and D2 will come in the forward bias. So when the input circuit will cross minus 10 value and will come to the minus 9, suppose let's take minus 9. So this is minus 9 and this is plus 10. It will be 1 volt kind of thing. So at the 1 volt, definitely the D1 will be in reverse bias, but D2 will be in the forward bias. Right? So this entire circuit, D1 will be off and D2 will work now. So how it will work and how the process will going on now, see the friends. Okay? See. Okay. Wait a minute. Now the maximum value, it will be at 10 volt. It will reach the 10 volt value. Okay. At this stage, the diode D2 is short circuited. Okay. And this C2 is going to charge over here. Okay. The max value is to 10 volt. Here is 10 volt already charged. What will be the V2? V2 will be 10 plus 10. 10 plus 10. It will be 20 volt. Now once it will reach to 20 volt, what will happen in the circuit now? Now once after crossing this 10 volt, when circuit will come to the negative half cycle, it will start, D1 will in the forward bias and this will be in reverse bias, and the situation or the condition will go like this. But what we have get over here, see, we get 20 volt over here, and in the voltage doubler we have seen that whatever the peak of the input, the double of the peak we are getting at the output stage. We are getting or not. Let's come the working over here. I'll read it for you. At the peak of the negative half cycle, D1 is forward bias. D1 will be forward bias. Okay. And D2 will be reverse bias. And this D2 will be reverse bias. This is the condition in the negative half cycle. This charges C1 to the peak value. This thing charges this C1 to the peak value. Okay, fine. Negative will be this side and positive will be that side. Okay, I'm okay with this. Now what next? At the peak of the positive half cycle, D1 is reverse bias and D2 is forward bias. Now this cycle is reached to the peak of positive half, plus 10. In the plus 10, this is plus, this will be off, and this will act as a short circuit in the circuit. So your entire circuit will be this. So because of this circuit, now you are going to charge the C2. D2 is forward bias. Because the source and the C1 are in series with C2, C2 will charge towards 2 Vp. As we have seen earlier, the C2 was charged by the 20 volt. Okay. So capacitor voltage increases continuously and finally becomes 20 volt. The voltage waveform is shown in the figure. I hope this is clear to you. See, the condition is, it's like this is the cycle kind of thing. Okay, at the output what you are getting is the condition. See, this is going to double itself. Is it okay? Or I can say you shifted it, because this is the input waveform. You add plus 10. Okay, you charge the capacitor. In the next stage, the equation was V in plus 10. Is it okay? And this was nothing but the VC2. Okay, and now we consider the max value of this 10 plus 10. Then that's why we were getting VC2 equal to 20 volt. Is it okay? So you shifted the waveform. It's clamping circuit. It's looking like clamping circuit or not. Now at the output finally you are getting the 2 of A. This is the capacitor. Capacitor is going to charge. Once capacitor is charged, it will maintain 20 volt throughout. It will maintain 20 volt throughout, because when it will be 20 volt over here, now this circuit will become off always. This D2 will be reverse bias always, because now you don't have power to come with more than 20 volt over here. So this will be in reverse bias, and your circuit or your capacitor will charge for the infinite time, and that you can take at the output stage anytime, 2 VR at any time, continuously you are getting. I hope you are getting me. Okay. So this is all about the voltage doubler. In similar way, we can triple the voltage, or we can multiply the voltage by n times also by adding n type of circuit. This is one circuit. Then one capacitor connected with this diode. In the second stage, D2 is connected with this. Like this will proceed. Here also will proceed. We'll add some more capacitors and diode circuit. Here I'll take the voltage output. So it will be tripler, voltage tripler. The output will be 3 times of Vm. Okay, so like this we are doing in the voltage doubler or tripler circuit. So I can give this another name, and that is the voltage multiplier. Okay, let's come to the Zener diode. Very important concept and very important diode. Again, I'm telling you, we are not going to the inside of this because this is not part of the analog electronics. If you want to study the Zener diode in details, you need to switch the electronic device and circuit. I told you earlier also. Because the detailed analysis of the devices is the part of EDC. For the EC people, I'm telling you. For the instrumentation people, you just follow the circuit and apply in the electrical circuit network, right? So, I'll tell you briefly what is the Zener diode all about. See friends, the diodes designed to work in the breakdown region. Actually, this is simple PN junction diode, no problem at all. I'm telling you about Zener diode to you people. Okay. And Zener diode is biased by the ratio 1 10 to the power 5. What is this? This is in the 10 to the power 5 atoms of the material, you are adding 1 impurity atom. Is it okay? So this is highly doped, I can say this is the highly doped semiconductor, semiconductor diode. Okay. So depletion layer in this will be very narrow. Why? Because this is the highly doped semiconductor or Zener diode. Okay. So friends, what will happen, this will work as a simple diode in the forward bias. The Zener diode, if you add this into the forward bias, or I can say in other words, if you bias it into the forward bias, it will work as a simple diode. But if you connect this as reverse bias, so we are getting something very interesting. And Zener diode is all about the reverse bias diode. The application of the Zener diode we are getting nowadays in the reverse bias only. In the forward bias, Zener diode is just act like a simple diode. Okay, we'll see the wait a minute, let me erase some parts. The diodes designed to work in the breakdown region are called the Zener diode. This we'll use in the breakdown. I'll tell you about breakdown also, because this is the important thing we are going to use in the circuits. If the reverse voltage exceeds the breakdown voltage, the Zener diode will normally not be destroyed as long as the current does not exceed the minimum value and the device closes not overload. Friends, see actually what is the point is, if this is the Zener diode circuit symbol, we are going to apply the Zener diode in reverse bias. We are using it into the reverse bias only. Let's take it VRB. So Zener diode has its own breakdown voltage. Okay, it's having its own breakdown voltage. It's in negative bias. So what is breakdown voltage? Suppose let's take the breakdown voltage is 5 volt. Means up to 5 volt, from 0 to 5 volt, the circuit will not work. As you've seen in the reverse bias, the diode is not going to conduct. It acts like open circuit. Okay. So the situation is like this. In the graph, if I'll tell you what you are going to do, you are applying the negative reverse bias voltage. We are increasing it. We are increasing it, and this is the current. Okay. So the reverse current, and what I'm saying is your voltage breakdown is 5 volt. Let's take it 5 volt. Okay. Over here. Okay. From this side, it will be definitely in the negative I'm talking about. So up to 5 volt, Zener diode will not conduct, zero current. Why? Because diode in the reverse bias. In the reverse bias, the diode is not going to conduct because it's facing very high current. R is high resistance, R is infinity, current is 0. But what is breakdown? Breakdown is the condition where this depletion layer will break itself. When it will be break, covalent bonds will be broken out over here, and you will get the abundant amount of, you will get over here some amount of electrons and holes pair. So those electrons will move into the circuit because of this external field, and you are getting infinite current over here. This is the situation like this. Now voltage will not increase. After breakdown, the voltage will increase in very small or very minimum value of the voltage, but current will be infinite. Is it okay? So this is all about the Zener diode. So we are going to use Zener diode in this region, VBR only. So let's see, can Can you tell me one thing now? After breakdown, this diode is working like, constant voltage device. After VBR, your voltage is fixed. Now your voltage is not going to increase, but your current is going to infinity. So your VBD is the fixed voltage across Zener diode. Means your Zener diode will do itself or will convert itself in a constant voltage source. V breakdown. Okay. So always the Zener diode is rated by its breakdown voltage. At the breakdown voltage, Zener diode will start to conduct. Before breakdown voltage, Zener diode will be 0. Later I'll tell you in details about this graph. Okay. So here just understand this. When Zener diode is forward biased, it works as a diode and drop across it is 0.7. This is the normal diode in forward bias. When it works in breakdown region, the voltage across it is constant, as I told you, by constant, and the current through the diode is decided by the external resistance. Thus, Zener diode can be used as a voltage regulator. We can regulate the voltage by using Zener diode in the configuration shown in the figure. For regulating the DC voltage, okay, so this is used for regulating the DC voltage. It maintains the output voltage constant even though the current through it changes. Okay, you have seen this. What is the, see, this is the Zener diode. This is the symbol of Zener diode, always like this. The simple diode is like this, but in the Zener diode you are making destroyed Z for Zener. Okay. So friends, if you'll observe this Zener diode I biased in negative. See, this is the negative biased or reverse bias you can say. Okay. Now in this question, or in this is not a question, in this graph they have given VZ, and I told you Zener diode is also given in terms of its breakdown voltage. VZ is the breakdown voltage of the Zener diode. It means at VZ, the Zener diode will break itself. Okay. So your condition is, you are just going to apply the VS. Here is the VS. In this I'm taking it VS. We are going to apply VS. You are going to apply VS. VS will start from 0 to VZ, then VZ to the next point. From 0 to VZ, here it's 0 to VZ. The current is 0 in the circuit, or I can say a very small current, that is the leakage current in the circuit, because circuit or diode is in the reverse bias. So in the reverse bias there is no current, or if you have the current in the practical diode, it will be very minimum, that is the leakage current or current due to the temperature. Okay. So here see, I equal to 0 in this region. Below breakdown, this is the condition below breakdown. After breakdown, once the Zener diode, the voltage across Zener is raised to VZ value, it's going to break itself. When it will break itself, the depletion layer will break itself and you are getting tremendous amount of electrons. So you'll be having very high current. Now the voltage after this stage, voltage is not going to change. Voltage will be that much only, but your current is infinity now. Your current is going to infinity, means very high current. Infinity means very high current, but this current will be decided by the circuit parameters, in which circuit you are connected the VZ. Okay. So this is all about the Zener waveform and characteristics. This is very important, and so many questions we are getting in the GATE exam from Zener background only. Okay. So let me take this one also. The load line of the circuit is given by Vs equal to Is Rs plus Vz. If you'll apply over here, see, if you'll apply your circuit loop over here, so you'll get Vs equal to Rs. This is the Rs multiply with Is plus Zener drop Vz. Okay. So if you want to draw the load line, you have to take Vs and Is. This is the Is, this is the Vs. Okay. Vs, Is. So here, how to draw the load line? See, your see, you are taking the, I think you can come directly over here. See, the load line is plotted along with the Zener characteristics. This is the Zener characteristics is given, and this is the characteristic in the reverse bias, but in the forward bias the Zener is working like a normal diode. So the load line is plotted along with Zener characteristics in the figure. The intersection point of the load line and the Zener characteristics gives the output voltage and Zener current. Is it okay to you? Let's come to the next point. The power handling capacity of this diode is better. The power dissipation of Zener diode is equal to the product of its voltage and current. This is the power dissipation, Vz and Iz. Whatever Iz is taken by the circuit or passing through the Zener diode, that current, and multiply with the Zener breakdown. Okay, the Zener breakdown will be fixed, but this current will change based on the circuit parameters. The amount of power which the Zener diode can withstand is Vz into Iz max. See, Vz is fixed for any Zener diode. This Vz is fixed, constant. Okay, let's take it K. What about Iz? Iz is depend on the circuit parameter or circuit elements, circuit resistance also, but still it has its own boundary, that is I max. After that the Zener diode will rupture itself. It will not work. It will be dead body after that. So Zener diode has its own limitation. If you apply the I max over, if you apply the I over the I max, the Zener diode will not work. It will fail to work because the power dissipation capacity will exceed, and the Zener diode will be permanently off. Is it okay? So friends, now I'll come to the Zener questions. We'll see some interesting problems, then we'll bind up this session. So this is gate problem again, and the problem is given as, I'll draw it in 30 seconds. This is 50 ohm connected with 10 volt battery. Here the Zener diode is given with its breakdown. The Zener diode will work always in reverse biased and given with its breakdown voltage, that is 6 voltage. 6 volt is given over here, connected with resistance R. Okay, this is the circuit, and over here the current I is given in the question, and what they're asking is, the option they have given is A equal to 1.2K, B equal to 50 ohm, C equal to 80 ohm, and D equal to 0 ohm. So obviously they're asking for this R only. So we'll read it. The 6 volt Zener diode shown below has 0 Zener resistance. The resistance of the Zener diode is 0 given in the question, and a knee current of 5 milliampere. Knee current of the 5 milliampere. Knee current is the current. See, in the characteristics we have seen this. This is the Vz, and this is the current at this stage is the knee current. Okay. The minimum value of R, you have to find the minimum value of R so that the voltage across it does not fall below 6 volt. You have to find the minimum value of R so that the voltage across R will not fall down below 6 volt. Is it okay? This is the question. So how to proceed it? Let me erase this part. This is the unnecessary part I have to remove. Now I'll proceed it. Okay. Let me change the pen color over here. So friends, they're asking what is the minimum value of R. So it can be with S10 to 6 volt only. See, 6 volt is given over this terminal, and this terminal is directly connected to the R. So over here also you have 6 volt. Is it okay? Now the question is, what is the minimum resistance? See, can you find out this I? Yes, you can find out, because here you have 6 volt, and this I will be, tell me potential difference 10 minus 6 divided by 50 ohm. Am I right with 50 ohm? Yes, it's 50 ohm, correct. So this is 4 by 50. Is it okay? So this is 8 by 100. So this is 80 milliampere. 80 milliampere is your current. Equation 1, let's take it equation 1. Now 80 milliampere current is coming from this side, 80 milliampere. Now at this stage, the knee current is 5 milliampere. This is the minimum current they are given with. This is the minimum current. If you want to work this Zener diode as 6 volt device, want to work with this, so you need to give this 6 milliampere. This is the minimum current in which in the Zener diode will work, right? It wanted the minimum 5 milliampere, then only it will going to drop 6 voltage across this. Okay, so the condition is this I, this is the I at this node. If we talk about, this is nothing but IZ minimum plus, if this is the minimum current, this is the load part, and in the load part I'm taking its IR. It's not multiplication of I and R, okay, will be max. Is it okay? If I will be max, why I'm going to take I max? Because they are asking for the R, V equal to Ri, right? V is fixed, we have to fix is 6. Now you need I, and you need the value of I mean. So if you want mean over here, you need max over here. Is it correct? I hope it's clear to you. So I need I max. You'll put I max over here, so you'll get I minimum. So this equation is perfectly fine for me. Now what is your I? You calculated 80 milliampere. Okay, fine. What is your IZ given in this question? 5 milliampere plus IR max. Again I'm telling you, you need max value, so you can get the minimum value of resistance. So IR max is 75 milliampere. 75 milliampere. Is it okay? So R minimum will be 6 divided by 75 milliampere. So this will be 6 divided by 75 into 1000. Okay. So it will be 80 ohm. So your answer is 80 ohm. Is it clear to you how to use the Zener circuit? How to use the Zener voltage drop? I'll take another problem. This is also gate problem, and the question reads as, you have 2.5K. Here you have two Zener diodes like this, connected in this way. Here you have V in perfectly fine, and here simply you are taking V0. The gate problem, this problem is gate problem. So here you are taking V0. This is your circuit all about. Now what is the question? 5 volt is given over here. This is 5 volt. This is 5 volt. You have to assume the polarities. This is the negative bias current. So plus will be this side, will be this side. It's like this. Is it okay? For a sinusoidal input, of 50 volt amplitude, 50 volt amplitude it is given over here. The circuit shown in the figure can be used as. This circuit shown in the figure can be used as. Your options are regulated DC power supply, regulated DC power supply. Yeah. Option B is given square wave generator. Square wave generator. Okay. Option C is given as half wave rectifier. Half wave rectifier. Half wave rectifier. And D is full wave rectifier. This is full wave rectifier. So let's check what is the working over here. See, input is the AC quantity, and that is 50 volt amplitude max value. So it's kind of this positive half cycle, negative half cycle. The max value is 50 volt. Okay. This is the input. When the positive half cycle will be here, here is the positive half cycle. In the positive half cycle, this diode will be in forward bias. Is it okay? So this will be in forward bias. because you applied the positive over here, and this will be in reverse bias. So your V in is max to 5, so definitely it will break it on diode Z1. So it is Z1 and Z2. This 50 volt is sufficient to the break Z1, and once the Z1 will be break, the voltage across it will be constant, and that is 5 volt. So this branch, in this branch we are getting the 5 volt at across Z1, and this is nothing but your output. In this circuit only 1 volt, so V0 is equal to 5 volt. Is it okay? So if I'll draw the waveform, this is your positive half, negative half of the cycle. The max value is given over here 50. Now you have to draw it. Okay. So friends, the question is you have to draw the output waveform. Okay. So in the positive half cycle, the diode Z1 will be in reverse bias, so it will be in breakdown region, and the breakdown voltage is 5 volt. But remember one thing, after 5 volt of the input only this thing will occur. So let's take the 5 volt of the input is over here. So up to 5 volt the circuit is off. Nothing, only input is coming over there up to 5. So we can neglect it. Just take it in the positive half cycle. In the positive half cycle, the output, this is the output waveform. For the entire positive half cycle, you are getting 5 volt as output. And in the negative half cycle, if we talk about the negative half cycle, this circuit will be in reverse bias, and this will be in forward bias. So this will, you will short it, and this will be having drop of minus 5 volt. So it will be minus 5 volt like this. So tell me which option is correct. Is this regulated DC? No. Square wave generator? Yes, absolutely right. This is the square wave it's going to generate over here. So is it clear to you? So friends, this is all about the today's class. We'll meet in the next with some more interesting problems based on Zener diode, and we'll wind up this entire diode circuit unit, and we'll switch to the transistor. Okay. So friends, one more thing I would like to say you, please do problems. You can prefer the GATE booklets, GATE problems, GATE previous year questions. It will boost up your knowledge and concept. Okay. So please do problems at your home. We'll meet in the next. Till then, take care and bye.